AC and DC motors part 4, synchronous motors. Today my topic is synchronous motors and I'm planning to explain you about the construction, operation, advantages and disadvantages, and what is the specialty of a synchronous motors, and how can you use a synchronous motor to control the power factor. So let's start. We are in the middle of a discussion about electrical motors. So far, we have covered AC motors, and there are two categories: asynchronous motors and synchronous motors. Asynchronous motors means the stator magnetic field and the rotor magnetic field, or the rotor speed. There is a difference. So always the stator magnetic field runs faster than its rotor. So we call it has a slip. So there are two kind of arrangement: squirrel cage and wound rotor arrangement. Today, what we are focusing is synchronous motors. Synchronous motors, the rotor has same speed like its rotating magnetic field of the stator. Right. So let's see what is the construction behind and how it operates. Let's consider this configuration: normal motor arrangement AC. It consists of a stator and a rotor. Let's say in this diagram, I have shown here blue and red, which means the rotating magnetic field. It represents north and south. Let's say if you supply the stator with an AC supply, there will be rotating magnetic field as shown. Then what happens if it is a normal induction motor? Due to flux cutting effect of this stator, okay, of course, as it rotates, it will cut the bars, the rotor bars, and there will be a torque produced on the rotor and it will start to spin. But the speed is always less than the rotating magnetic field, so we call it has a slip. That is the difference between synchronous speed and the difference between the rotor speed. Yes, as a percentage of the synchronous speed, if you consider it as, we call it as slip. In synchronous motors, this is a big difference. We know in induction motors, to spin the rotor, there should be induction takes place, and because of that induction, there is a torque. That's why the rotor starts to spin. So there is always a slip between these two. If there is no slip, no induction takes place. And as I mentioned earlier, in synchronous motors, there won't be a slip. It's just like if you see that rotor is spinning at the same speed of its rotating magnetic field. So there won't be any relative motion between these two magnetic field, so that the stator magnetic field never cuts the rotor conductors. So there won't be any EMF induced, so there won't be any torque produced. So then how it keeps rotates? Okay, that is the specialty of synchronous. Okay. So far, what we know, in synchronous motor, rotor speed is exactly same as the stator rotating magnetic field, and there is no slip. Okay, then let's reveal how it operates. This is the basic construction of a synchronous motor. It has a stator and it has a salient pole construction of same like a synchronous generator. Synchronous motor and synchronous generator are almost similar thing, only this device work done is two different way. The synchronous generator, we drive the rotor by using a prime mover and take the output as electrical energy. In synchronous motor, we supply electrical energy and we get the work done as a mechanical movement to turn or spin some load. Right. So stator winding is there, and a rotor, it consists a winding same like as a alternator. We called its main field winding. You can supply a DC supply, so then there will be magnetic field north south. And the problem is, let's say you have a north south magnetic field here and the rotor is stationary because that you supplied a DC supply externally. And if you supply a three-phase supply to your stator winding, there will be rotating magnetic field. Doesn't matter, you have a north south magnetic field and there will be a very fast moving rotating magnetic field. So this rotating magnetic field never grab the rotor magnetic field and hold it, and will be able to drag the rotor along with it. There will be greater slip, still that your rotor will in a uh, stationary position. It will never start spin, unless or otherwise you first drive the rotor by external means. You have to drive the rotor by external means, then it will have inertia. So now it's under rotating situation. Then if you energize this one, it's apparently this rotor magnetic field also be rotating, and there will be difference, the less difference between this stator magnetic field as well as rotor magnetic field. In that condition, there's a possibility the stator and the rotor different polarities lock together, and thereafter continues to spin to maintain the spin. So that is how a synchronous motor starting takes place. So what is the construction? It has a wound rotor construction, which means it has a salient pole coil. It has a commutator, so then you can supply a DC supply through the commutator, and it has a stator windings where you are going to supply three-phase supply. So this rotor we call the armature, because there will be DC excitation also will takes place. And so this is the construction, right? What we know, the synchronous motors construction same as alternators, right? And it has no slips, no EMF induction, no torque produced, so they are not self-starting. So let's see how these motors are started. Okay, so the previous case that what we saw is it has a commutator and slip ring arrangement, but there are some brushless synchronous motors also, and they are most favored and less maintenance that you can do, because you do not have brushes and slip rings, so no wear and tear. So the brushless excitation is there, same like your brushless alternators. This is the simple basic arrangement of such. You have main stator winding where you supply the three phase, and you have the rotor main field. From this rotor that you can see, you will have plus and minus, because there is a rectifier. This rectifier is subjected to a exciter rotor, and there is exciter stator where you supply excitation variable voltage, that you supply excitation voltage. There will be AC supply, so rotating magnetic field will be there, and from this rotating magnetic field it will cut the rotor exciter, and it will induce rotor magnetic field also an AC supply. Then this AC supply pass through a rectifier diode, and it will convert into a DC supply, so plus minus. Then there will be magnetic field. This magnetic field and this stator rotating magnetic field, different polarities, they will lock together and starts to or maintain to continue run only if you drives the rotor by an external source. So this is the brushless excitation. You can see no any brushes consist in this area. So this is the similar arrangement. This is a much more clear view. I mean to say, this is the main stator, this is the main field, and the diode bridge, rotor, exciter rotor, it supplies the DC supply, and this is a three-phase excitation supply. There are permanent magnet synchronous motors also. In that case, you do not have any wound rotor or salient pole construction on the rotor. It has a permanent magnet. So they are very simple construction, and they are inexpensive. But the problem is, as it is the permanent magnet, the excitation cannot be vary, and so mostly a small application that you can find three-phase permanent magnet synchronous motors. They are usually typically 100 watt to 100 kilowatt application that you can see. There is no winding, no exciter, so it is robust with compared to the previous. The drawback is there is a demagnetization of after some time with the aging, because if it is a permanent magnet. Right, let's move to the starting method of the synchronous motor. As there is no induction takes place, there is no torque produced, so they are not self-starting. So now this is the arrangement that you are going to use. This is your synchronous motor. It has a stator and a rotor. This rotor is supplied with a DC supply through a slip ring and using an exciter which is connected to the same shaft. This exciter is a DC exciter and variable supply. So you can supply plus and minus. So, and this is the shaft where it connected to a load. This load may be a propeller, maybe a pump, shaft, whatever. And you can see that special, there is a special arrangement we can see here, a pony motor. This pony motor is nothing more, it is a simple induction motor. The small induction motor which used to drive the shaft. So because we have to bring the synchronous motor up to some speed, then only the magnetic field of the stator winding and the rotor will lock together and maintain the rotating movement. So the pony motor is a small motor. As it's small motor, it cannot drive a large load, handle load. So normally there is a clutch arrangement that which disconnect this thing, or otherwise there should be unloading arrangement like zero pitch arrangement. So then the pony motor can drive the entire shafting arrangement. Let's see how this works. Initially, okay, there are two contactors. You supply main supply initially, you just, let's say if this one is K1, only the K1 is energized, K2 is de-energized. So the pony motor get powers and starts to spin the shaft. Because as the shaft starts to spin, the exciter, it will produce a DC supply, a variable voltage excitation supply, let's say plus minus. From this DC supply, a magnetic field will create on the main rotor north south. And because of this magnetic field, there will be a magnetic field, a rotating magnetic field. This magnetic field will cut the stator winding and it produce a back EMF, same like in case of generator, EB. And it is a AC supply, EB. Still this contactor is not open. And now you have EMF here. Let's say now this pony motor brings both that your synchronous motor to the rated speed. Normally what is the design? The pony motor designed in such way its full speed is slightly greater than the synchronous speed of this synchronous motor stator winding. That is the arrangement that is designed by varying the number of pole pairs of this pony motor. So it drives this shaft slightly above the synchronous speed of synchronous motor, right? Okay. And because of this back EMF, now we are in a bit difficulty because you cannot close this breaker. Okay, now it's running at the synchronous speed, just above the synchronous speed of the synchronous motor, but now you don't want to run the pony motor. You have to decouple the pony motor and give the power to this stator. But as there is a EMF and your supply voltage also having some kind of volt, we can say that is V. These two phases, there are two supplies of on both sides of these contactors. This is from back EMF, this one is from supply. And who knows whether they are in phase or out of phase. If they are in phase, no worries, there won't be any spark or something that you can keep closing the breaker. So you have to use a synchronizing lamp arrangement to make sure, external synchronizer to make sure when you are closing this breaker, the back EMF as well as the supply is in phase. Once it is confirmed that they are in phase, you can close this breaker. So there will be north-south magnetic field created on this stator winding, and these two magnetic field will lock together and maintain the rotor speed. And that time you can disengage or disconnect the contactor for pony motor. Thereafter, pony motor is no use. Right? Okay, this is the basic arrangement of pony motor starting method. Now let's see the second method of starting is using as an induction motor. The synchronous motor can be started as induction motor, but you need special construction for that. Okay, this is the normal stator winding, and the rotor, it consists of salient pole arrangement, and this blue color, okay, these windings are the main field winding. Now what is the special arrangement here? You have damper winding sets. There are two winding sets consisting this rotor. One is a squirrel cage. This outer winding or damper windings looks like a squirrel cage induction motor, the same construction. And the inner winding, that they are the excitation main field windings, right? So you have to supply these windings. It has a commutator or brush or slip ring arrangement, so the blue one, right? Okay, now how that these motors are get started. Initially, let's say you are not supplying the excitation or the field winding is not energized, right? I did mistake here. This field winding, the blue arrow should be come down, come below. I will do the correction here. Yes, this one is the field winding and this one is the damper winding. Yes, damper winding, right? Okay. Right. Let's say at the beginning, what we are going to do, we are going to stop, or we are not going to supply the field winding. And then the damper windings, what they will do, they act as a normal induction motor. So what induction motor does, as the stator rotating magnetic field is there, there is a closed circuit path in the damper bus like a squirrel cage. So it creates a torque. Because of that, there will be an EMF and circulating current in the rotor. So it creates a torque. So then the rotor starts to spin. And it drives the spin with a slip. And it takes closest to the synchronous speed of this synchronous motor of the stator, right? And after some times what you do, once it comes to the rated RPM, then you supply the field winding with the supply, DC supply, right? And this will cause that the rotating magnetic field of the stator and the main field winding different polarities lock together and continues the rotation, and it will pull the rotor into synchronism. The main stator field will pull the rotor into synchronism, so they will be the rotor will spin at the same speed as the rotating magnetic field of the stator. At that time, there won't be any induced EMF on the damper bus because there won't be any relative motion between these two. So no flux cutting is the winding will cut by the flux of this rotating magnetic field of the stator. So there won't be any induction takes place, right? So thereafter, while running position at the running condition, the damper winding sets, they just act as a damper, which means a damper. If there is increment or sudden load changes, there will be fluctuation of this RPM in a synchronous motor. It's try to get out from the synchronism, out of synchronism. So let's say in case of increment of the load, what happens? The rotor tends to slows down. If it is if the magnetic field is not, if the excitation is not enough, then it tends to slows down. In that case, whenever it's tried to get slows down, there will be induced EMF in the damper set of winding because it's a squirrel cage arrangement. Then it will give additional torque. It will provide additional torque. Again, it helps to pull back the rotor into synchronism. Yeah, this is the basic principle of the second starting method. This is the most available starting method of synchronous motors because there is no polymotor arrangement, synchronizing arrangement or such thing. A bit simpler construction. The third method of the starting is start the synchronous motor as a slip ring induction motor. The slip ring induction motor, it has the stator winding. All these stator are the same construction. The rotor, it has a special arrangement. The rotor is a wound rotor. So these wound rotor motors, how they are starting, the reason to use a wound rotor is normally to increase the starting torque, because the starting torque of an induction motor depends on the rotor resistance. So in wound rotor, the rotor coil is connected to external resistance bank for starting time. For starting time, that you set the highest resistance value and you start the motor. So once the rotor picks up its speed And once it's overcome the starting inertia and this thing, that you are gradually reducing the starting resistance. So the running performance of the starting motor, the induction motor comes to considerable or acceptable range. This is normal wound rotor starting method. So the wound rotor motors are self-starting because they have closed path to move this circulating current in the rotor. Right, what we are doing with when we running this motor as a synchronous motor. So okay, first you start it as a normal wound rotor motor. Then after some times you change over this switch from the resistance band to excitation, a DC supply. This DC supply, you can see these two windings, these first two windings are getting the common negative supply, and the third winding get the positive supply. So it acts as a north-south, a fixed permanent magnet like electromagnet. And then as the rotor already was running in at the closest to the synchronous speed, once that you supply its excitation, the stator magnetic field pull the rotor into its synchronous speed. Then both rotor and the stator magnetic field will run at the synchronous speed. So this is how the third starting method with slip ring starting induction motor takes place, right? Okay. Okay, there are three methods of starting that already discussed. Let's move to advantages and disadvantages of synchronous motors. Synchronous motors, actually they are very easy to control the power factor. Yes, you can increase and decrease the excitation, so then you can control the power factor. Let's see in later part how you can do this. And the speed over the load range, it is maintained constant because the stator winding as well as the rotor is locked together. Doesn't matter how much load is applied, that they are locked together and there is no slip. But in normal induction motor, whenever the load increases, the slip increases. Here no slip. It the stator winding always tries to drag the rotor with its synchronous speed. Disadvantage is the cost is high, and rotor need external excitation system and special arrangement need for starting. Okay, these are the disadvantage of synchronous motor. Let's see how to control the power factor. Now this is the familiar, right, the previous pony motor starting method. I have shown this back EMF and the supply voltage. Let's say we are saying that under excitation of this motor, when you adjust your excitation to the rotor field, if the back EMF is less than the supply voltage, we call it is under excitation. At that time, your current lacks the voltage, which means you consume the power from your supply. It's considered like that. So in that case, the motor runs as a reactive load or lagging power factor. If you provide the right amount of excitation, you adjust the excitation to give where that EB is equal to the supply voltage, we said that it is under normal excitation, or the motor said to be run as unity power factor. Whenever EB is equal to V, how you control that? Controlling the excitation. And overexcitation. The overexcitation is the one whenever you increase the excitation, that times EB increases greater than the supply voltage. That time your current lead the voltage. So the motor is said to be running as a leading power factor or over excitation. And this is how that you are using a synchronous motor to control power factor of a bus bar. We call a special device when we are using this synchronous motor in the application of power controlling, we call it synchro condenser or synchro compensator. So mostly you can see in shaft generator system which are thyristor operated, you can see synchro compensator or condenser. It's nothing more or less same synchronous motor or synchronous generator, where by varying your excitation that you can change the power factor. And whenever you see a normal synchronous generator motoring or reverse power takes place, so the generator run as a synchronous motor. Actually, it is not a harm situation that much because it's act as a normal synchronous motor. Only thing that there is a danger if you continues to use, because there is no use, only power loss, and the other part, the running or the healthy generator may get overload if there is any problem. And the major risk is if there is your power prime mover, any safety activated from the mechanical side, it won't stop. Even it will not, even the fuel cut off, it will not stop because the alternator will drive the prime mover. Okay, that I will be discussing in the generator protection session. So this is about the synchronous motors. I hope that you guys enjoy the video. So if you have any problem or if you have any proposed videos, you can comment in the section. I will be uploading more videos, and please subscribe, and thanks for being with me.